Hello and welcome back, everybody. The title of this section is Matrices and Matrix Multiplication. So let's just take a quick step back and recall that our motivation for linear maps goes back to the Schrodinger equation, and really everything from this semester goes back to that. But in particular with linear maps, it was this h hat on the right-hand side that we are focused on. I mean, technically, the derivative is also a linear map. You saw that really briefly in an earlier video. But really, we're trying to understand these objects. So we're going to understand these as best as possible. And matrices are the best perspective we know of for linear maps. So really, matrices are a perspective that you take on linear maps. In fact, they're a representation of linear maps. We'll see that soon. And they really give us a good collection of tools, or maybe a good collection of intuitions on how linear maps behave. And so that's why we're going to focus on matrices for really the rest of the semester. So let's go ahead and see what a matrix is. So I'll just make a definition of a matrix. A matrix is a two-dimensional array which represents a linear map. Now, I'll comment here. It's certainly common in mathematics and definitely outside of mathematics. Almost everybody will refer to two-dimensional arrays as matrices. I don't do that. I'm probably in the minority. And really saving the word array to be an array and the word matrix to be specifically an array which represents a linear map. So when I refer to matrices, I'm only going to call them a matrix if they're associated to a linear map. However, a lot of people will refer to matrices as just the arrays themselves, independent of whether or not they're associated to a linear map. So that's just a slight caveat to my language versus everybody else's language. It shouldn't make a big difference in this semester, but maybe it'll make a big difference if you try to tell somebody that a matrix has to represent a linear map. In a lot of cases, it doesn't. It's just my perspective that it has to represent a linear map. So I'll just say with those matrices there, matrices as referred to by everyone else. But anyway, it's a two-dimensional array which represents a linear map. What is a two-dimensional array? What do I mean by that? Dimensional array. And really, it's an array of numbers. So it would be like the real numbers or the complex numbers. This is going to be just like with vectors, where you could use the large column with some parentheses on either side. An array is just a column with two directions. So it has a row and it has a column. And in fact, there's multiple rows and multiple columns, and then parentheses on either side. So we would have number, 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 number. For example, we'll say RC are these entries. That's what an array looks like. You've probably encountered matrices in previous courses. I know I encountered them the first time I was in 10th grade, I think. So these are the sort of thing that people do scatter into even high school mathematics as well. But what does it mean to represent a linear map is, we'll do it, for example, the matrix 2, 1, 1, 0 represents the linear map L of x1, x2 equals 2, 1, 1, 0, where those are the coefficients of x1, x2, x1, x2. And they get added horizontally. So we could write this a little bit easier as 2x1 plus x2, and then just x1 in the second coordinate. So that's a linear map, and the matrix is basically these four numbers represent the four coefficients in the output. So I'll write that out here. The entries in a matrix, I'm going to say often, in parentheses, represent the coefficients of the output of a linear map. Now let's make this a little bit more formal. Given a linear map L from a vector space to another vector space, the matrix representation of L is a doubly indexed set. Right? This is where indexing comes back into play, and in fact there are two indexes to a matrix. I'll write it as M, and it's going to be doubly indexed by the letters I and J, superscript and subscript, and I and J are going to start at 1, and they're going to end at the dimension of W and the dimension of V, respectively. And this doubly indexed set, the entries Mij, are going to be defined by the inner product of L against Ej, and then the entire inner product is against Fi, where the sets Ej, J going from 1 to the dimension of V, and Fi, I going from 1 to the dimension of W, are orthonormal bases for V and W, respectively. Now this is incredibly abstract, and in fact a lot of undergraduate courses never even touch on this sort of a statement, but it is quite useful. This is an incredibly useful statement, as it says the following. It really says the following. You start with a linear map. You then establish an orthonormal basis for the domain and codomain of our linear map. And then in step 3, you gain a matrix for free. It's not completely free because you do have to perform calculations. You have calculations of inner products. But you could imagine, given a computer or something, you gain it for free. Now, a lot of people are wondering, here was a great matrix that represents a linear map. Why can't we just grab coefficients? And you certainly can. You can definitely grab coefficients in the most basic of situations, which is probably a lot of them we're going to encounter in this class. But what's really cool about what we have here is that there's nothing restricting my vector spaces to be, maybe the d-dimensional complex numbers or the d-dimensional real numbers, but rather we can do this with, well, what was a common one that we keep showing up with in this course would be like quantum states. These are quantum mechanical states, for example. Or other cases, we could have, function spaces. So I'll just write it as a capital F, which is a space of functions. And in fact, something like the operator ddx, the actual real-life derivative operator, could be L in a function space. So there's a matrix which represents a derivative. And that's incredibly useful. We're going to see that kind of thinking about any sort of linear operator as a matrix will be incredibly useful. So let's go ahead and use this formality in just one example. I'm really not going to stress it too much in this course, but let's do one example with this formality. Let's say, for example, consider the linear map L, whose input is R2, and whose output is this space of quadratic polynomials that I like to refer to sometimes. So this is like the space ax squared plus bx plus c. And R2, of course, is one of everybody's favorite. Let's just call it x1, x2. And so let's consider the linear map given by L of x1, x2 is, let's do 3x1 minus 2x2 x squared plus 2x1 minus x2x minus x2. So now this is a little bit confusing because I got, x's here and x's here, and those are not the same x's. So maybe I'll make our lives a little prettier and call these ones a and b instead, because two-dimensional vectors can have whatever names we want them to have. There's a 2 there. So if I put an a and a b there instead, I can say 3a minus 2b, 2a minus b, and minus b. So let's call this space a and b instead. And all I need to do, so to find a matrix representation for L, we need an orthonormal basis of R2 and P2. And we're going to consider P2 as a subset of the Taylor series, more or less. So the orthonormal basis can just be x to the 0 power, x to the first power, and x squared. And R2 is really easy. We just construct it canonically, 1, 0, 0, 1. And as I was just saying with P2, as long as you consider the inner product as the Taylor series inner product, which we saw in an earlier video, that can be x squared, x, and 1. And so all we have to do is we need to compute the following. We compute the inner product of L of 1, 0 against the image 1, and then we need the inner product of L on 0, 1 against 1. We need L on 1, 0 against x. We need L on 0, 1 against x. We need L on 1, 0 against x squared. L on 0, 1 against x squared. So let's think about computing each of these. What is the image L of 0, 1? Well, that just, or 1, 0. That just means I'm putting a 1 in for A and a 0 in for B. So 1, 0, 1, 0, 0. So if I go through all of that work, it looks like I just have 3. This will be 3x squared plus 2x. So that means that's the same for all of these. 3x squared plus 2x and 3x squared plus 2x. The image of 0, 1 will be a 0 here and a 1 here. So I've got a 0, 1, 0, 1, 1. Looks like I'm going to have a negative 2x squared minus 1x minus 1. Negative 2x squared minus x minus 1. Negative 2x squared minus x minus 1. And let's recall what these inner products mean. These inner products extract the coefficient on that term. So the inner product against 1, we're looking at the coefficient of 1 over there, which is 0. The inner product against 1, we're looking at the coefficient on 1, which is negative 1. The inner product on x, we're looking at the coefficient of x, which is 2. Against x, the coefficient is negative 1. Coefficient on x squared is a 3. The coefficient on x squared is a negative 2. And now you can finally see what the matrix is, because the matrix is just going to be the collection of these 6 outputs. Our matrix representation is 0, negative 1, 2, negative 1, 3, negative 2. Now this may seem like a bunch of meaningless junk, but we will see how this comes into play not only in the next video where we go through some worked examples, but also just in the rest of the semester. So that's what a matrix is, and we'll talk about why matrices are useful now. Let's actually say, why would we ever use a matrix? And the primary answer to this is composition of linear maps. So this is like function composition. So let's consider the following. Consider L1, a linear map, which takes x1, x2 to 2x1 minus x2, x1 minus 2x2. And let's consider L2, which inputs, let's say, y1 and y2 now, and it outputs 3y1, and it outputs negative 2y1 minus y2. So those are two linear maps. They have a composition. Let's recall what this means. They have a composition which would be defined as, on x1, x2, would be defined as L1 on the output of L2 of x1, x2. And L2 is going to move x1, x2 to the vector 3x1, negative 2x1 minus x2. And then if I plugged those into L1, what I'm looking at is that goes in for every copy of x1. So both those copies of x1 are going to be considered as 3x1, and this is considered as every copy of x2. Which means that my output here will be 2 times 3x1 minus the bottom, which is negative 2x1 minus x2. Then my second entry is going to be 3x1 minus 2 times the bottom, negative 2x1 minus x2. And if I go ahead and simplify this, it looks like I've got a total of 6x1 plus 2x1, so I've got a total of 8x1 here. And then I also have a positive x2 here. And then in the second row, I've got 3x1 minus negative 2 copies of 2x1, so 3x1 plus 4x1, it's going to be 7x1. And then minus negative 2 copies of x2 is going to be plus 2x2. So we see what I ended up with is also a linear map because I have only a linear combination of each of the inputs, x1 and x2. But in fact, these numbers, 8, 1, 7, and 2, came from somewhere. Right, if I jump back up to my original 2 linear maps and look at kind of the matrices that would represent those, 2, negative 1, 1, negative 2, and 3, 0, negative 2, negative 1, that's just me extracting coefficients. There's a 0 there, negative 2, negative 1. How does this 8, 1, 7, 2 come from the 2 previous matrices? Well, we have something called an operation called matrix multiplication. Explains how what I started with, my 2 matrices I started with, 2, negative 1, 1, negative 2, and 3, 0, negative 2, negative 1 can be related, so we just use a dot for that, can be related to give me this output 8, 1, 7, 2. Now how is this defined? Well, it's actually defined based on taking every row on the left-hand side and every column on the right-hand side and performing all, perform all possible inner products of rows on the left with columns on the right and place the output in the space where they overlap. In that sense, I mean, in this case, if I want to take this row with this column, I'm going to take their inner product, which would be 2 times 0 minus 1 times negative 1. And so I'm going to get, 0, 2 times 0 plus negative 1 times negative 1. I'm going to get 1, and I'm going to check where they overlap. They overlap in this coordinate. So I'm going to take that output, I'm going to put it in that coordinate. And then I can repeat, right? So suppose I repeated with my bottom row and my first column. My bottom row inner product, my first column would be 1 times 3 plus negative 2 times negative 2. And I'm going to get 3 plus 4, which is 7. And I'm going to go ahead and look at where they overlap. And they overlap right at the 7, and so on. So this is what we're going to do. It's going to be what I've just circled. And that's going to define matrix multiplication for us. So I'm going to go ahead and make the remark. So the primary remark of this, really the rest of the semester, okay? The rest of the semester, our primary remark is that we can efficiently calculate compositions of linear maps by first representing them as a matrix, and second, performing matrix multiplication. So that's really what we want to think for the rest of the semester, is that these linear maps, which to us are just everything that object in Schrodinger refers to, we can perform its compositions. Now you may be wondering why I want to perform compositions of this. The real reason is that we try to invert it. So keep in mind an inverse is a special case of composition. So in reality, what we're going to end up trying to do is learn about it through its inverse. But we're going to get there by representing it like a matrix and then performing matrix multiplication. Okay, so let's make this matrix multiplication clearer one more time. So we'll actually define it now. So two versions of definitions. Let's make the most straightforward one, but perhaps harder to calculate, done first. Given two matrices Mij and Njk, the matrix multiplication is Mij and Jk considered as Einstein summation. So that's quite efficient. Keep in mind, as Einstein summation, what would this look like? This would look like the sum over j and whatever index set j is in, call it capital J, m sub j, n to the j, and then we just have our I over here and our k over there. So it's that set. And then, of course, that set would now be indexed only by two entries, I and k. So since it's indexed by two entries, hence a new matrix or a new linear map. So that's like the really effective way of computing these matrix multiplications. But the way you should think in this course, the multiplication of two matrices is what I've already described. You consider all columns and all rows, and then you compute all possible inner products of columns with rows and place the resulting number where the two overlap. Let's run some of these examples. Let's do 3, 1, 2, 1, 0, 1, and we'll multiply this by 1, 2, 3, 3, 2, 1. And you'll notice that the sizes are different, and that is perfectly allowed as long as, say, different sizes are fine so long as the row, column, inner products still make sense. So let's recall what we're supposed to do here. We take all rows on the left and all columns on the right, and the inner product still makes sense because the size of this row is the same as the size of this column all the way through. And so we should be good to go. Let's consider the overlap between this one and this one. That's going to be overlapped in the top left. Right, so top left, I'm going to have this inner product of 3, 1 with 1, 3. The inner product of 3, 1 with 1, 3 is 3 times 1 plus 1 times 3. Then we move on. The inner product of 2, 1 with 1, 3 is 2 times 1 plus 1 times 3. The inner product of 0, 1 with 1, 3 is 0 times 1 plus 1 times 3. And then we just continue. So 3, 1 against 2, 2 is going to be 3 times 2 plus 1 times 2. 2, 1, against 2, 2 is going to be 2 times 2 plus 1 times 2. And then 0, 1 against 2, 2 will be 0 times 2 plus 1 times 2. Finally, 3, 1 against 3, 1 will be 3 times 3 plus 1 times 1. 2, 1 against 3, 1 will be 2 times 3 plus 1 times 1. And 0, 1 against 3, 1 will be 0 times 3 plus 1 times 1. And the output is just me actually simplifying everything. I've got 3 plus 3, 6. I then have 2 plus 3, 5. 0 plus 3, 3. 6 plus 2 is 8. 4 plus 2 is 6. 0 plus 2 is 2. 9 plus 1 is 10. 6 plus 1 is 7. And 0 plus 1 is 1. So that is the resulting matrix. What I can do here is I can note now that the two linear maps, let's say L1 of x1, x2, whose outputs are given by the coefficients here. So the outputs would be like 3x1 plus x2. Then you would have 2x1 plus x2 and 0x1 plus x2. So that's the first linear map. And L2, which takes 3 inputs in and gives 2 inputs out. So I'm looking at here for coefficients. So 3 inputs in, x1, x2, x3, and it gives me 2 outputs given by the coefficients up there. Those coefficients would be x1 plus 2x2 plus 3x3, and then 3x1 plus 2x2 plus x3. If I have those two linear maps, the composition L1 on L2 of x1, x2, x3. Note that the input here is the input to L2 because it needs to go next to L2 in my composition as well. Has an output given precisely by what I've just calculated. So it's given precisely by those 9 numbers: 6, 8, 10, 5, 6, 7, 3, 2, 1. And all I have to do is write x1, x2, x3, x1, x2, x3, and x1, x2, x3. I think if I had asked you to perform the composition, you could have done it, but it would have taken you quite some time to arrive at all of those coefficients. And so this is how you can see that really getting used to matrix multiplication can make your life quite quick, quite a lot faster than if you were to do everything by hand. So let's look at one last example. Let's do a matrix multiplication of a linear map and its inverse. Okay, so in the last video, I tackled a linear map and its inverse, and those were the following. They were that the linear map L on x1, x2 was 2x1 minus x2 and x1 minus 2x2. And then we had calculated and actually proven that its inverse was 2/3 x1 minus 1/3 x2, 1/3 x1 minus 2/3 x2. Let's see what this looks like as matrices and matrix multiplication. So let's go ahead and compute L inverse x1, x2, and L inverse L x1, x2 as matrices instead. Well, to do that, we just start with the kind of the representations of each of them, which would be me looking at the 4 coefficients, which is 2, -1, 1, and -2. And I'm just going to go ahead and multiply by L inverse, which was 2/3, -1/3, 1/3, and -2/3. And then I go ahead and perform the matrix multiplication. The matrix multiplication, recall, is all rows against the column, the row against the column, and all combinations of those. So let's go ahead and look. The first row against the first column gives me 4/3. That's just that term times that term. And then this term times this term is -1/3. If I do the first row times the second column, I get 2 times -1/3 and -2/3. And then -1 times -2/3 is +2/3. If I do that again with the bottom row, I have a 1 times 2/3. And I have a -2 times 1/3, so -2/3. And then the bottom right, I have 1 times -1/3. And -2 times -2/3 is +4/3. So if I go ahead and simplify all 4 of those, what do I end up with? I end up with a 3/3, also known as 1, and then 0, and then 0, and then 3/3, also known as 1. And so what we see here is that inverse matrices lead me here. And so what is this? What is this object? It's got a couple names. This is called the identity matrix and has representation. Let's say the identity matrix is often called capital ID. We use capital letters for matrices most of the time. It's got a representation. ID is a set, right? Every matrix is really just a doubly indexed set, and this is exactly the Kronecker delta function that we've been dealing with the entire semester. This is just the dimension of whatever vector space I'm in. So there's the Kronecker delta. Because why is this a Kronecker delta? Well, if the row and the column are the same, that would be I and j being the same, then I'm a 1, and if the row and the column are different, then I'm always a 0, which is exactly a Kronecker delta. Anyway, we'll analyze that object a lot more in the next video. I'm glad you stuck with me through this one. I'll see you in the next one. Bye.